This isn't just another electric surfboard. While the shell was purchased, the core propulsion system was entirely designed, assembled, and installed by me. From the battery pack and Inrunner motor to the metal 3D printed screw, this system was built from scratch by hand. Before building anything physical, I created a detailed 3D model of the drivetrain. I optimized the layout for waterproofing, vibration isolation, and thermal dissipation, and checked for cable clearance and internal spacing in CAD. The motor I used is the Run 70125S D560 kV Inrunner, capable of delivering up to 10 kilowatts of power and over 25 Newton meters of torque. It's built for high-speed operation and sealed to survive tough aquatic environments. The ESC is the Esrun Max 4HV 300A with a 300A continuous rating and up to 1870A peak. It's waterproof and equipped with full protective circuitry, making it ideal for high output marine applications. To validate the propeller, I performed CFD simulations on the custom metal screw I designed. Rather than chasing maximum efficiency, I focused on strength and thrust. So this wasn't just assembly, it was precision orchestration. Every component had to be installed, aligned, and sealed with care. I started by applying a thin, even layer of grease to the motor shaft. In saltwater conditions, corrosion and wear happened quickly, so metal on metal contact must be properly managed from the beginning. Next, I mounted the 3D printed metal screw. Because of slight tolerances from the printing process, I had to fine fit the shaft coupling manually, repeatedly aligning and checking clearances. Even a slight misalignment could cause vibration at high speed, leading to performance loss or even damage. Then came the motor housing. Since Inrunner motors generate a lot of heat, I use a housing with built-in cooling fins. Waterproofing was handled with gaskets and silicone O-rings. And instead of rigid mounting, I focused on achieving a balance between secure fitment and vibration absorption. With the mechanical assembly complete, I wired up the system. I connected the ESC throttle signal wires and sensor cables, making sure everything was routed neatly and physically isolated from moving parts. All connectors were sealed to keep out moisture. The most critical waterproofing point was the coupling between the motor shaft and the main drive shaft. Since this junction rotates and sits near water, I applied a large amount of grease to this area. The grease not only reduces friction but also acts as a barrier to water. I checked the coupling pressure several times before closing it up. Once wiring and sealing were complete, I ran a final system check. I powered on the ESC, moved the throttle slightly, and the screw began to spin. Seeing all of it come together and work exactly as intended was a satisfying moment. To me, this wasn't just assembly, it was tuning. Every part needed to move in harmony, and that took intuition, precision, and engineering. After verifying that the drive system worked, I mounted it to the bottom of the board. I aligned the frame, added vibration damping spacers, and sealed everything down with screws and silicone. From the outside, it may look simple, but inside it's a dense mechanical system that I designed and built myself. And this board is no longer just a shell. It now holds a fully functional, hand-built electric drivetrain. In the next video, I'll design and build the battery pack that powers this board and put the entire system through real-world testing. If this video was interesting or inspiring to you in any way, I truly appreciate your like and subscription. This channel is all about making what others only imagine and showing you every step of the real engineering that makes it possible. See you in part 2.